here is how I think of the world. I think, and that's how we think about the world since roughly 1920s. You cannot think of time, which we will do in this course, throughout the course, as separate from space. We live in a space-time. Now, in special and general relativity, this is a very precise statement of symmetry of space-time called Minkowski symmetry. But even without that symmetry, that's how you have to think about the world. And now, in this space-time, there is no preferred time and there is no preferred direction in space. And what you're supposed to do when you're describing the law that you have, the law is usually written in some differential form in here that says that when I look at any neighborhood of my space-time and I nudge something in some direction, that's called a differential. There's some basic things that have to be conserved, like mass, energy, God knows what. So if I nudge it in some way, let's say forward in time, in space-time, I have to compensate for it by terms in space, and there might be some forcing terms I have to include in this, and there might be some nonlinear terms, and the whole course is about nonlinear terms, really. And that's what these equations that people hand to you, like Newton's equation, look like. But that's not what you need to know. You need to know that when you look at the whole world, space-time, you have to enumerate possible outcomes consistent with this law. These things are called orbits or trajectories. And then you have to, and it's like book of life. Each one of them will have a name. And they have longer and longer names. Eventually, this book is infinite when you start resolving it in very fine detail. But there's a coarse approximation, indicated in this little plot. So first, you'll have to find in this world, these are the possible things that can happen. So that's like a book of life. These are possible lives. But then you'll have to also say, well, some lives matter to me, some don't. There is something, so you'll have to learn how to give them a relative weight. And today we know how to do that, but I cannot teach you that in this course. I can only teach you baby steps. So I'll start with, first baby step, a differential equation. And even before that, I will start a little bit more abstractly, but I won't be abstract for the end. I have to tell you what is the subject. And I'll first define it in abstract ways. But hopefully that makes sense to you. So we are given a world. For example, in Atlanta, I am at some location. I have some identity. There is some temperature. And of course, in that particular case, it's very hard to define my state. But in physics, chemistry, biology, we tend to go to simpler elements, and we can say we have a particle at some position, at some state. So I have to specify, spatial coordinates, maybe temperature, whatever comes up in my problem. And the idea is that if there is a set of, hopefully finite set of numbers, that if I give them to you to arbitrary precision, I've specified the state. So there is something called state space. There is also history, call it the phase space, but I don't like the word. I think engineers say state space and it's more descriptive. This is some relic of mechanics and wave mechanics, phases or waves. And this is, the world of possible states. So there's an M. I will start with M, which is one-dimensional, so too simple. But in general, this is something in many dimensions. And in that state space, there are states. There are things that are conceivable, allowable. And we can say that, there is a particle at coordinates, x, y, z, little ones, with some temperature, some velocity, and some finite list of properties. And if I have a complete list, I've defined a state space. For example, if I give you only 3 numbers, but I don't give you atmospheric pressure, you cannot predict weather. But if I give you sufficiently many data points, you can start describing what might happen. So this is state space. Then there is the law. That sounds very authoritarian, but the law is imposed on us by usually some basic principles of symmetries and conservations of things. So the law usually makes sense. And there is a part of it that's arbitrary and requires experimentation. So Newton's gravity is an example. The potential might have been different, but eventually, Hooke invented it, Newton stole it, he made it a law, and eventually we have agreed that this is extremely good law to describe what happens if I have a state. So the law is some definite rule. Let's say we call it F. And what the law does is take state X and acts on it and produces, another state X prime in a world of allowable states. So now if there is unique outcome for every initial state, that's called determinism. Now, it could be something else having to do with probability, so it's not stochastic, not noisy. Everything is assumed predictable. And it's not quantum. Where also we don't have precise prediction of positions and velocity specifically. But we assume it's deterministic, so the thing they have in mind is, Newton's law describing planets. In principle, that should just work. And now these two things are called dynamical system. So there is a state space and there is the law. And if you give me 2 of these things, I can now go and start working out the consequences of the law. So this is how we abstractly think about it. And applications of the law, what it does is it generates trajectories. So if I start any place and I apply my law, I will end up someplace in the state space. And now, depending on the precise nature of the law, I will be able to draw something that we call a trajectory. Now, if you think of, let's say, celestial mechanical system, or if you think of a fluid in a pipe, some form of turbulence, then you as human, see these things in three-dimensional space, and you see what happens to them in one extra dimension, which for you is Newtonian time, separate from the space. But this is not how you describe the state space. The state space will give you full description, which means if I have 4, sun and 3 celestial bodies, I'll have to specify position of all of them. So I'll have to use 3 positions or 4. I'll have 12 coordinates there. But then I won't be able to predict anything unless I tell you in which direction and how fast they're moving at that instant. So I'll have to double this to 24 dimensions. And that's a state space. And then if there's some symmetries, like you can translate the whole world, you can choose a direction, you can get rid of some of these dimensions. But basically, the state space tend to be high dimensional. In this course, it'll be 1, 2, 3, maybe more, but not much. And if you, visit our labs at 3rd floor Howie, or 5th floor where people do numerical simulations of fluids, there might be 50, 100, 200 million dimensional, because you'll have to describe lots of particles moving through. And today we can do this. We are way beyond what Poincaré could do. So now the first thing that we learned from this determinism, everybody has unique trajectory. I'm in a state space. So what that means, that the moment I have the law, original state space was points, infinitely many places I could be to get started. Is my problem. But the moment I add a law to it, it becomes a ball of spaghetti. And this is, close to my picture I was trying to tell you before, how we think about it. The important thing is that it's now divided in possible life outcomes following these possible trajectories. And it turns out our job is to enumerate this and to decide which ones are how important. So that's what dynamical systems do. Now, being very optimistic, you can now say, well, I'll write down a universal computer program that solves all dynamical systems. It's kind of cute of you to think about, but you're saying that, I will describe all laws, known or unknown, possible state spaces. So very quickly you discover that this is a fool's errand. Nobody can do that thing. So this is not going to be the right way to do this. So the way it really works is that, there are problems. For example, you're interested in fish swimming and moving water, and that's a PhD. You're interested in monkey wanting to move a hand, a beautiful nonlinear problem in high dimension. That's a PhD or a bunch of PhDs. So in the practice, it turns out all problems are hard. And what we want to give you here is not the solution to all problems conceivable, but a set of tools that you can use today, but people in Poincaré's time, they were not accessible except to Poincaré himself, but only on the abstract level. Set of practical tools which will enable you to do biophysics, chemistry, atmospheric science, climatology, quantum field theory, particle physics, general relativity, black hole physics. They all share some common tools, and that's what we are supposed to teach. So now these dynamical systems come in two convenient varieties. The one is that you're indoctrinated in since time of Newton and Leibniz, saying that, if I'm in some state, there is a law that says what happens delta t, where time, delta t is arbitrarily small period of time. And in continuum limit, there's infinitesimal things. I have a continuum trajectory, which I obtain by integration of my laws, as we will see later. The other thing that turns out to be equally and maybe more useful, but not natural to physicists, is that you can look, at a disco full of people, and instead of looking at them all the time, you could strobe them. You could find out where they are at given time intervals. In that case, dynamics is not continuous lines, but it's points, and points are connected by so-called maps. So there is nothing that says that laws of nature should be written in this way, just that we are mostly used to, state them this way, but we're not necessarily solving them this way. So the thing that seems very natural to us is to think of everything in terms of differential equation, this kind of education that we have. And the idea of differential equation is that we are given something in continuous time. The law is stated, the law of your particular PhD thesis or undergraduate project, is that if I am someplace in a state and I want to see what happens in infinitesimal time, so you think of the displacement in infinitesimal time of your state point, your particle flowing in this phase space, that's some kind of velocity. These x's are not necessarily length, but this is like length over time. And you can say the law is stated by saying that every place, at every point, I know where I'm moving and at what velocity. And what I mean by x is always, in this course, a finite number of dimensions. That's now one way to define a dynamical system, because if every place at every point in my state space, I have this function, this is a velocity. You can think of it as some kind of vector of the same dimensionality of your space. So this is now what's meant by f of x. And what that thing is saying is that if I'm any place in my space, a manifold M, that's why I call it M here, it tells me that every place in the space I can move one step. Now, the laws can be linear and nonlinear. And it's kind of a weird situation because they always teach you linear laws first. And I really hope you had a linear algebra course because it's totally crucial for getting started here. Even though our goal is to teach you how to deal with a typical problem, which is almost always nonlinear. There are very few genuine linear problems. But linear problems are pretty good. So for a linear problem, what you say is that my vector field velocity, but generalized to arbitrary state space, where different directions have different dimensional meanings. A linear one says that the law is simply that I take my coordinate 1 and I have some velocity in that direction, and then I take my second coordinate and I go to last coordinates, xn. And this thing is not so stupid. I mean, it really, for example, our intuition, the first intuition about how mechanics should work comes from Hooke, who said, well, if I press something, this thing will move a little bit. If I press it twice as hard, it'll move twice as far. And this was indeed true for kind of things that he was looking at, springs or rods. They responded proportionally to the forcing. And that's called harmonic oscillators, which you learn a great deal about. So linear systems are not so silly. I mean, they're quite useful. Many applications like computing interest rates and banking, etc., they can be, at least in start, these are linear problems. Or problems can be nonlinear and have some form that beyond terms like this, which are linear terms, the law also depends on combinations of how hard I'm pushing in two directions, let's say x1 and x2, and so on. So the response of the system, it's not just where I am, but it kind of depends, it resists in a way which are not proportional to the displacements, but they could be some power of the displacement. And you would think, well, okay, big deal, we can solve all this. What's the problem? So now it turns out that the quintessentially modern thing that happened in 1970s and 1980s, that's not done by Poincaré and other people a century earlier, is something called renormalization theory. And how did we get into renormalization? We said, well, okay, the simplest nonlinear thing should be, x squared, right? So I should be able to understand everything about x squared. It's a parabola. Well, it turns out it's incredibly rich problem. It leads to this renormalization. Earlier today, I was at a conference in Nice, France, at a dynamical systems conference for this European Dynamical Day. And one of the talks was about renormalization of something that's only quadratic. And, a man who does it has a tenure at the university because people are spending lifetimes understanding and proving such problem. So it turns out nonlinearity is a very hard in the sense that, lots of them you have to kind of approach individually, but there are certain ways how to approach them. So that's my goal and Strogatz's goal here. And the first thing we want to tell you is that when you are given some problem, you should think geometrically. Now, what does that mean? You're given some stupid set of equations, of which you'll see lots in this course and lots when you read the paper. And you look at these equations and you have no clue what these things are doing. So then advice is to, step a little bit back and just try to understand qualitatively what kind of thing, what's going on. And later on, if you understand qualitatively what are the possible outcomes described by these kind of equations, you can come back and do the detailed calculation with any precision. But it's a hopeless task if you don't understand what kind of things can a given system do. Here is a nice example, very simple. Let's take a one-dimensional system. So we live only on a line. X takes the values between minus infinity and plus infinity on the line. The state space is only the value of where you're on the line. And you see this very often when you shine light on something or you have a pendulum. Your velocity has to do with some trigonometric function, which usually means that, if I'm going this way, my component along the direction x is small or big, depending on what the sign does. So, this is by definition dx dt. Then you can say, well, multiply both sides divide, and I get that dt is dx over sine x. Then you integrate. Now you know how to integrate differentials here. So you put integral sign on both sides. On the left-hand side, you get indefinite integral, which is just the end of this thing. And on the right-hand side, you get something that says I should look at dx. And then the stupid function 1 over sine x has a name, because traditionally, every time you don't understand something, you give it a name. So this is cosecant. And then, you look someplace, somebody teaches you, and they tell you, yes, this integral we can do. And the result is the logarithm of absolute value of cosecant. The integral goes from x0 to x. So it's a cosecant of x0 plus, and I'm cheating because I don't remember this answer, I'm just looking at it. Voila, that's the answer. It's exact, it can be done analytically, but what does it mean? But it's one of the few things you can actually integrate it, and that's the answer. And so now what? So I have the answer. Now today, you can plot it in Mathematica or MATLAB or whatever you like to use. But it's not very satisfactory. Now, this is a baby example. There's something in physics called Ising model, which is what happens when you have many little magnets, if you wish, sitting on an array, two-dimensional array, interacting with each other. And physics question is, if I heat this up, will they freeze or will they do something? So that's called statistical mechanics. And that, during the Second World War, a very smart person with lots of time on his hands in Trondheim, Norway, analytically solved it in terms of some weird functions, which all have names because we don't understand what to do this. So the answer was known, but it took a very good physicist who doesn't understand formulas but like to understand what he's doing, called Leo Kadanoff. It took someplace until late 60s, early 70s for this person to have a kind of picture that I'll try to explain how we solve this, understand this particular problem. Even today, having analytic solutions of the 19th century type, if you understand what they mean, can get you to a Nobel Prize. So, how do we understand what this means? So understanding what it means is, we would like to know what kind of trajectories can one have qualitatively. Can I just tell you, in this problem, this kind of thing can happen, without actually computing it to arbitrary numerical precision. So here how it works for, x dot equals sine x. So in higher dimensions, I drew a picture for you saying that this kind of thing is a vector field, meaning that if I'm in n dimensions, then velocity is also n-dimensional. It's pointing in any direction there. Now, in one dimension, you don't think of it as a vector, but that's what it is. It's a special case. It's a vector field, one-dimensional, but understanding that actually helps you quite a bit later on. And now what you can draw, let's see, I'll cheat a little bit because I'll need some open circles. You can draw your line, which is your world, your state space, what I call manifold M, here just a line. And your state on that line is described by a single number called x. But now, nobody forbids me to introduce a new dimension in this case, which I call x dot. And just plot what this velocity looks like for every x. So sine of 0 is 0, so I know it's going through 0. I know it kind of goes up. Then it has to come down. And when we get to value pi, my velocity was positive here, but now it changes sign, it goes negative. And at 2 pi, meaning I've gone a full circle in some sense, even though this is an infinite line, I go up, and this repeats itself, right? So now, and of course I have to draw it also for negative values of x. So that's my velocity field. I've drawn it by hand. It's a very inaccurate representation of the velocity field. I might have to compute it to 17 digits in some, optical cold physics problem, but here it's good to 5%. But here is the qualitative thing. Velocity is positive, which means that I'm any place here, my vector field points this way, vector field. And I go faster and faster until this point. And then I go slower, but all the way I'm moving in this direction. Now, if I started at some initial point like this is negative, so I have to go back. And now you get a drift of it. Here I go forward, backward, forward, backward. So what does that mean? The most important thing is whenever I have a dynamical system, and that actually is the first thing you will always have to check. It's a little bit counterintuitive. You're interested in motions, things moving, but the first thing you have to figure out are the points in state space which are not moving. They have many names. So they're called fixed points. If at one of these points, velocity is 0, right? X dot equals 0. So I don't move. Or they can be called equilibria. That comes from thinking about pendulums. So if pendulum hangs, then equilibrium is going this way. But if you try to keep it upright, it's infinite precision. There is a point where pendulums just stand up, and that's equilibrium point. Difference between two of them, that perturbation up here, moves you away. The perturbation down here makes you just wiggle around the field. So there are two kinds in one dimension. It gets more complicated, higher dimensions. They are the ones which are stable. Or people say they're attracting. Or people who think about fluids, they think they're like sinks. You just go in there and that's it, you're lost. And there are unstable ones or repelling. Sometimes in engineering, when you're sending field theory, etc., when you're sending some stuff in, you can do it by this mechanism. You can be a source of stuff, sources. And now, honestly, you know everything you need to know about this system. And now, if you want to, you can compute it very precisely. But, looking at this answer, you had no clue, what are cosekines doing? Obviously, the important values have to do with multiples of pi because you're looking at trigonometric function, but you have these ratios, absolute value, logarithm of God knows what it means. Here it is. That's what it means. So that's the brilliant idea that Poincaré, and that's what happens very often. In retrospect, brilliant ideas are very simple. It was almost offensive to professional mathematicians and physicists, theoretical physicists around the 19th century that, their very deep knowledge of special functions can be replaced by some child's sketch of what they do. But that knowledge is very powerful. So, so now when you know this, you can go and, understand what that formula means. This formula, you can, sometimes useful, sometimes not. You can paint what's called a phase portrait or state space portrait. So what you can do, knowing what this thing is, you can actually look at where are you in phase space as a vertical axis as a function of time. And, you have 0 and pi. Remember, those were the important things here. 0, pi, 2 pi, etc. Now it's a vertical axis. And if for some reason, totally arbitrary, somebody asks you, well, I started at power 4, what's going to happen to me? Well, you know the following thing. You know that this is attractive fixed point. And, perhaps disappointingly, you have very limited life options. You start someplace at pi 4. This picture says all that can happen to you will fall into this hole, the sink, the attractor, and that's it. You'll never get to the other side. Nothing else will happen. Somewhat boring, but good start. So my trajectory will be, I start here. I start falling toward the attracting point. But then as I come closer to it, velocity slows down, and that's what this logarithm is doing. So I'm getting my trajectory in space-time. It's going to the attracted point. And if I put a little more detail to it, so I say, well, I want to start with lots of points between pi and 2 pi, let's say. Then what will happen is that all these points will do this kind of thing. And because this is determinism, they're never allowed to cross each other. So they'll be just bunching up, running away for repelling point. And on the other side, they'll be all doing the same thing. But if I start here, I have to go in the opposite direction. So this is understanding what a formula means. To me, the formula, and that's true almost all formulas. Now, there are different kind of people. So my choice in childhood was, should I be a painter or a mathematician? Now, nobody wanted painters, but they seem to be more interested in paying salaries to mathematicians. So I decided I'll become, theoretical physicist for some random reason. I never understand this, never. I mean, it's just a bunch of symbols coupled with a phase portrait or, qualitative picture of the dynamics. This thing here, I'm in a saddle. I know what it is. So that's how science works for me. There are people who really think in formulas, and more power to them. Just not one of them, but I very much appreciate it. So one thing we have learned so far is that, fixed points seem important. But that's not the end of the story. We also have to know about their stability. So what's a fixed point? If I have my velocity field denoted F. Right now it's one-dimensional, but it could be in any dimension. So it could have 7 components. In state space, there's some very special points where nothing happens. And nothing happening means that if I'm there, there is no motion, there is no dynamics. Velocity is 0. They're super important. So how do you find those things? So I'll just take one of the Strogatz examples. Let's take, equation like this one, just a little bit different. So you say, well, x velocity is proportional to where I am. You might already guess that this is going to have a exponential as a solution. This is basically, the solution to all linear problems. But no, it's a nonlinear problem. So I subtract from it something that oscillates with x. So where is the fixed point? Well, one way to do this is to plot both functions. So this is the first function. So this first function is just 45-degree line because, my height is proportional to where I am. So this is x equal y line. And the other guy is the cosine. So at origin, it's 1. And then at minus pi over 2 and plus pi over 2, this thing is 0, being a cosine. So it looks something like that. And then, does its own thing. And condition that x dot is 0 means that they have to be exactly the same. So there is a special value right here where these two things are the same. And basically what this says is that over here, the cosine is more important than sine. So in this region, the velocity is negative and I'm moving this way. When they exactly meet, I'm in the equilibrium. But when x is larger than equilibrium, then I have to move away. And this goes on and on and on. And I find out this is a rather boring system. It has an unstable fixed point here. So this is, what happens in the state space. This is x dot for the two functions separately. If I'm exactly at this point, I don't move. If somebody kicks me a little bit off this point in either direction, I just run away to minus infinity or to plus infinity. And because this is a little wiggle and this is very big, it's going to be dominated by exponential solution with little corrections to it. Okay, that's actually all I want to say for the first lecture. Now the course has its tempo, which is we would like you to solve a problem set every week. It won't be very hard. The reason why we do this is because in this subject, unless you actually do this yourself with your fingertips, you understand nothing. The way I understood nonlinear dynamics was exactly this way. When I was being deprogrammed from quantum field theory and learning this new subject, I had a little machine made by Hewlett-Packard, which spewed out printouts because I didn't have a screen, and I plotted all these plots I'm showing you now, without benefit of Strogatz. He's a Johnny come lately. I have to warn you about, this is an old subject, old book. You know how to use internet. You can get all the solutions of anything you want. The wonderful thing about Strogatz is the 20% of problems are wrong and the solutions are wrong. So good luck to you. Chris knows the wrong ones. So if you're just mindlessly copying some crap from internet, be ready to meet the wrath of Chris. But it's up to you. You've been warned. We will not tell you which 20% are wrong. Also, you might want to hear Strogatz give the same lecture. He's really good. So, okay. If no questions, I will go on to my daily things, which is late taking a paper. Bye.